So this talk is really about Java's unsoundness, and if you take nothing else from it, the proposal here is to fix it by making sure that every wildcard in Java has a witness type, and we'll talk about exactly what that means. But we found that to be precise enough to roll it out across Google. So we're going to have to go through sort of the background on Java's unsoundness a bit before we dive into what we're doing about it. So bear with me for a little while. So Java's unsound. We found out about this at OOPSLA, here at OOPSLA 6 years ago. And in that paper, they walk through sort of a series of examples that compile, but then when you run it, they fail with class cast exceptions, even though they shouldn't. They show examples for both Java and Scala. There was a paper on nullness types in Scala 2 years ago at OOPSLA, at eCoop, I'm sorry, that suggests you can use nullness types to fix Scala, but Java and Scala actually have different reasons for why they're unsound. Here we're focusing on Java, and we're also going to use a different fix than there. In this talk, I'm also going to use a new example, but you can see how the previous examples play out in the paper. Okay, so here's the example. I understand this is sort of a wall of text, but Javac accepts this. It'll just compile it. But when you run it, you get a class cast exception here that says string cannot be cast to marker. Marker is an interface that we're introducing here. Let's see if this works. Yes. There's a marker interface here, and then there's also this type converter that has a type parameter bounded by marker. And a type that you're going to see throughout this talk is this converter question super T type here. But in any case, what happens is that the string that I'm passing in here, at this point, needs to be cast to marker, and of course we can't do that. All right, so this slide won't make a ton of sense at this point, but hopefully it will make more sense later. There's certainly different ways of fixing this. One is to kind of make sure that all wildcards that you can express in the language are sort of correct by construction. Another is to do something similar to what Scala did and use nullness types. But in this paper, we're going to try to do something different. So let's talk a little bit more about the background here. And the background here is really around wildcards, because wildcards is sort of a necessary ingredient to run into the unsoundness. So generic types in Java are invariant by default. So list of integer is not a subtype of list of number, nor is it a supertype. But there's wildcards, so you can do fun things like you can say list of question mark. So that's just a list of some unknown type. And you can also say things like list of question extends number, and that sort of expresses covariance, right? So list of integers are actually a subtype of list of question extends number. And you can do the same thing with list of question super number to express contravariance. In the literature, usually we think of wildcards as existential types. So there's some X, and then we have some constraints on it here, and then we have a list of that X. Right? Now, also in the literature, when we look at existential types, there's usually an implicit syntactic form to introduce an existential type. There's many ways of writing this, but here's one, and it has this thing here that you see this star integer here. That's called the witness type. That's the type that the programmer is saying that they want to the existential variable that's being introduced here to stand in for, right? And this is actually pretty great because it gives the type checker an opportunity to check that these two are really consistent. And so here, for instance, we can check that integer is actually a subtype of number. In Java, you're probably aware there is no introduction form for wildcards. Instead, the Java language specification has an algorithm that's sort of designed to make sure that there is a witness. It doesn't compute the witness, or it's not specified, but it makes sure there is a witness. So in this case, these rules, they say, OK, so list of integer is a subtype of list of question extends integer. That's pretty straightforward. And then list of question extends integer is considered a subtype of list of question extends number, and that's how we get the desired result here. But also in the JLS, it says null is a subtype of anything. So that means you can also kind of introduce wildcard types sort of through the back door. All right. Now, dually, we want to also eliminate wildcards, right? And so again, if we look at the literature for existential types, there's usually an elimination form, like a let binding or something. And it's pretty nice actually, because you can refer to the type variable here in the second expression. But again, you saw this coming in Java. We don't have that. Instead, Java has capture conversion. So if you have a variable with a wildcard type here, like list of question extends number, and you want to call get on it, question is, what type does that have? Well, so what Java does is it generates a fresh type variable, like x here, and then it can type the result with x, right? And it also, you can see, introduces sort of the constraints that come from the wildcard. In this case, that x is a subtype of number. OK, so in practice, though, Java wildcards, we can think of them as kind of an existential type with an upper bound and a lower bound, which in this paper we write as lower dot dot upper. Now, very often, the lower bound is bottom, so there isn't really a lower bound. But if you use question super, then you can specify a different lower bound. And the upper bound is also often object. But you can specify it either with explicitly by saying, question extends number, for example, or otherwise it can also be inherited implicitly from the type parameter that the wildcard stands in for. So if you remember our converter question super t here, because converter is defined to have an upper bound here, right? That wildcard really is an existential type with the upper bound marker and the lower bound t. Now, most of the time, we know that the lower bound is a subtype of the upper bound. But there are cases in Java expressible where, in the context where it's declared, we don't know this. And in this paper, we're going to call those wildcards subtype asserting wildcards. It'll become a little bit more clear why in a second. But I posted a snippet of the code example that we looked at earlier here with our converter type, and then our converter question super t here. That's a subtype asserting wildcard, because t here doesn't have an upper bound. And so it asserts that t is a subtype of marker, even though we don't otherwise know that. All right. So now let's take a look at our example and why it goes wrong. All right. So here's a line of code that throws an exception, right? So how does this thing type check? So the compiler will do a capture conversion here. So it'll introduce a fresh type variable for our good friend wildcard here, call it w. And then it's actually going to use that as the type argument for our wrap object that we're constructing here. And once it does that, it says, all right, well, in order to call handle, we now need a w, right? Because that's how handle is declared. And if you substitute w for t, then that's what you get. And it turns out, well, our input variable here of type t is a subtype of w. Why? Because we just assumed it right here. Right? This is saying t is a subtype of w, so this type checks. OK. So in principle, that's OK, depending on how t is instantiated, right? So t is a type variable itself. So depending on how it's instantiated, that might not be a bad thing. But still, you might ask, how would one be able to introduce one of these converter question super t's here? All right, so let's take a look at that next. So this is where we're introducing it, right? So we declared it as a field here that gets initialized in the constructor of our input class. But then when we call the constructor, we just pass null here. And that, if you remember from before, also type checks, because null is a subtype of anything. And so JavaC just kind of takes this. It says, all right, no problem. And so taking those two together, we can now, if you look at this here, t is an unconstrained type variable. The compiler will let us instantiate that as a string, and then we can pass in a string, and it blows up. All right. So the class cast exception occurs where the capture conversion happened, so during wildcard elimination. And in other proposals, there's sort of previous proposals for how to approach this. One is to sort of limit the allowable wildcards. So you kind of limit what you can say. So for instance, in the OOPSLA paper that reported the unsoundness, they say, you could only allow question super wildcards if the upper bound is object, if I understand correctly what they're proposing there. Or you can do something similar to Scala. You could do something like require questionable wildcards to be non-null, right? Because you also do need null in order to exploit this, as I showed. Our approach is a little bit different. It is to just simply require that all wildcards have a witness when they're being introduced, including from null values. And so by that, we are allowing subtype asserting wildcards, but we prevent their introduction without witness. And so with that, this statement here would just fail because there's no witness here that we can provide at this point. And so then suddenly this code doesn't type check anymore. OK, so great. Let's try to formalize that. Turns out that's a bit of a to-do because we kind of got to build up enough machinery to express all of this. So we started with featherweight Java plus tame of J, which is an existing formalization of wildcards as existential types. We admit subtype asserting wildcards because we need them, and null. As in Java, in the formal system, wildcards are introduced implicitly through subtyping, but we actually use a let expression to make capture conversion explicit. And you'll see in a second that that's kind of convenient to do, actually. But it's just a technical device, basically. And then the key change to other type system is the typing of null. Right? Normally, we would just allow any type here. So Java would allow any type for null values. But we're instead requiring a precondition here that T be witnessed. And a witnessed type is either a type variable in our system, any type without existential type variables, meaning a type without wildcards, and then any type that has a subtype that is witnessed. And the last one just admits basically any wildcard except subtype asserting wildcards. OK. Now, why type variables? Considering all type variables to be witnessed, it just lets us type null as a type variable, right? And that's helpful, for instance, if you try to implement a generic container like a map. You want to implement map.get, which sometimes returns null. And this way, you can type it as the value parameter type of the map. All right, but so we need that for expressiveness, but in return, we unfortunately have to do some other things. So we need to require witness types in a few more places, namely when we construct new objects, in generic method calls, and also in extends and implements clauses. All right. So with that, we can go about proving type safety. Now, preservation basically goes through. It takes a while, but it basically goes through. The property that's arguably difficult here is progress. And I'm showing the evaluation rule here for our let binding given a null value. And if you think about it, it kind of needs to come up with a type substitution here for the existential type variables that I'm eliminating. And so the question is, can I come up with that substitution? If I can't, then I'm stuck and there's no progress, right? So we have this lemma we call witness lemma that guarantees us that we can generate this substitution if we have a witnessed type. And the requirements I showed earlier, they guarantee us that we have this, right? So by requiring witness types for null and also for new expressions, we know we're always going to have that. And so then we can prove progress. All right. So now you might ask, OK, well, how does this work out in practice? I certainly was curious. So we implemented this as a static analysis in error-prone, which is a Java C plugin. So it lets us look at Java C's internal AST after the type checker is done and just kind of scan it. We just walk it. And we look for subtype asserting wildcards where nulls are being assigned, and also in these other places that I mentioned. This is open source, and it is also part of Google's build system Bazel. And as such, we were able to just roll this out across all Java builds at Google. So that's a lot of lines of code of Java, several hundred million lines of code. And we didn't actually find any code that ran afoul of Java's unsoundness. There were no null values in the code base that introduced subtype asserting wildcards. The analysis did flag a single file with a type argument that had a subtype asserting wildcard in it in a generic method call. So it's very easy to fix. I'm going to show this in the next slide. But that is the one false positive that we found. So here's the sort of a simplified version of that file. Looks pretty familiar, hopefully, because I actually used this to derive the example that I showed earlier. However, this is safe. Nothing goes wrong here, right? But the analysis flags this call to stream here and says the inferred type argument, programmer didn't write it down, and you can't because it would fail. The infer type argument is converter question super T, and it's subtype asserting. So in this case, this was very easy to fix, actually, because this is in a private inner class. So all we had to do was declare an upper bound for the type parameter T here, which we can easily do because the public method that instantiates our class here already has that. And so the compiler just accepts this, the analysis is happy, and then we were able to roll this out. The other thing we did was look for sort of, wildcards in the code base. So we sort of ran variants of this over the code base and sort of looked for whether there are any other subtype asserting wildcards and so forth. So this is across Google's monorepo, several million, 100 million lines of code. The numbers you see are per 100 million lines of code, roughly. And you can see there's about 3 subtype asserting wildcards per 100 million lines of Java code. So very few, but they are there, right? But if you pull back the precision a little bit, so this is all about question super wildcards. In the first line, subtype asserting. In the second one, we're just looking for them with any implicit upper bound other than object. And you can see you get orders of magnitude more. And then if you just look for any upper bound, including object, you get at least another order of magnitude more. So this is the false positive that I mentioned earlier. This I think corresponds to what was proposed in the OOPSLA paper, if I understand it correctly. And you can see that in Google's code base, this would actually be pretty common. Like it's like once every 100,000 lines of code, it would break something. But if you go a little bit more precise, if you just focus on subtype asserting wildcards, that, as far as I can tell, is sort of what Kotlin does based on sort of playing with it. It just doesn't let you declare subtype asserting wildcards. And I think for a new language, I think that's pretty reasonable. Like, it's going to very, very, very rarely get in your way. And so they were able to just avoid the problem with that. OK, so I promised you would see this slide again. So here it is. So, there's a few approaches potentially to fixing Java's unsoundness. There might be more. One is to kind of make all wildcards correct by construction. That seems to be what Kotlin does. And you saw in the table how that plays out in practice. You could also sort of use nullness types, similar to Scala, I think. But we don't have nullness types in Java, and clearly that would be quite an effort to introduce. Or we can restrict the typing of null. And the other thing that's interesting about that is that technically, this allows sort of some programs that nullness types wouldn't. So like here's our example again. In order to fix it, all we kind of have to do is declare this upper bound here, t extends marker, and then the compiler will no longer allow us to call doConvert with a string, right? And so we can still pass null here. So our converter question super t can totally be nullable. That's not a problem. We never dereference c anyway, so it doesn't matter that it's null. And so the difference here is simply that, like in our approach, we focus on actually guaranteed null values, whereas with a nullable type system, the value can be null or non-null. All right. So in conclusion, we can fix Java's unsoundness by limiting null values and a few other places to witness types. And that ensures that every wildcard, when it's introduced, has a witness type. There's a formalization in the paper that you can take a look at. And then I showed you some results of how this plays out in Google's repo. Thank you.
Thank you. Questions? So we have the order of the questions. Thank you. And you can answer from the one in the middle. Thank you.
Hello. Yes, just curious if this would work with Scala. Or...
I don't know. So, like I said, Scala's unsoundness is different from Java's. So I am not sure if you would be able to take a similar approach there.
So did I get this correctly, that Java should actually try to prevent something like that happening? So the type system of Java should prevent that such type of exceptions are thrown, but it didn't. Is that about right?
Yes. So this code, so Java-C accepts it, right? That is to say, it just compiles it. There's no typing errors. There isn't even warnings. But then when you run it, it fails with a class cast exception. But there aren't any casts in the program. So that really shouldn't happen. Right? If there was a cast here, if I had written like cast to marker, yes, sure, I can get a class cast exception. But I didn't, right? So if Java was sound, then this shouldn't be possible. If the compiler accepts it, it should run without class cast exception.
Have you looked at creating a JSR?
I have not. The paper only just got published, in my defense, though.
Absolutely. No, I mean, this is cool. It just feels like Java should just do this.
Maybe. I mean, I think no matter what you do, I think, there could be code out there that you're going to break. And so I don't know how feasible it is to do in the language. The data from Google says that in practice, it will have very little impact, or maybe even none at all, depending on how much Java code you have. But in the meanwhile, you can use our analysis or use Bazel, and then you sort of get the safety anyway.
Yeah, that's great. I mean, I guess my impression is this is probably lower impact than a breaking change to a library, which doesn't happen a lot in Java, but certainly happens and causes people trouble. So yeah. Anyway, I hope lots of people use it.
Hi, so nice work. So I don't know. I'm not sure I understand all the details, but coming from a Haskell background, this strikes me as similar to how the type constraints embedded in a JDT value can only be made available after you pattern match on them, right? So which seems similar.
Okay.
Based on that intuition, I would expect that you should be able to insert a kind of dynamic null check at the point where your potentially non-satisfied constraint is introduced into the typing context. Would that make sense? Or
maybe. I don't know that I fully follow that, but so there's a few things to say that I think I don't have good slides about that, but it's discussed in the paper. So let's see. So first of all, as this example shows, sorry, not this one. I apologize. This one. There isn't actually anything bad about null. So you don't really need to do a null check per se. It is fine here to introduce, our null here still introduces a subtype asserting wildcard down here, right? Because T is unconstrained here. So this is still a subtype asserting wildcard, and it's fine to introduce that. It's just that where we're introducing it, and it's fine to pass null for it. It's just that where we're introducing it, we know that it's, we made sure that it's not dangerous. And the other thing to note is that Java generics are erased. You may have heard about this. So at runtime, the runtime doesn't actually have access to any of the stuff in angle brackets here, right? So there's nothing to check at runtime.
Very nice work. So I haven't really followed the past literature, but wasn't there an issue also with undecidability with question mark super?
With understandability?
With question mark super with lower bounds. Wasn't there also can't you simulate a Turing machine or something? I thought that there are more reasons to constrain question mark super than just the unsoundness.
I think that's true. There is some papers on the undecidability of that. That's certainly also true. Yes.
Okay, so maybe an alternative proposal, just like the original paper, might prevent more than just the unsoundness. But you were also very cautious the way you described what your understanding of the original approach or of the original limitation from the Tate paper. You were saying, as far as I understand it, this is what they're proposing. So I'm guessing you haven't really asked the authors, right? Because the way you described it sounds pretty understandable, even like to me. So you don't have upper bounds except for object.
So I have not asked them. This is true. Though I would love to talk to them. So the OOPSLA 2016 paper is mostly about the unsoundness. So there is one paragraph in there that sort of sketches some possibilities for what one might do. And so I told you what my reading of that paragraph is, and hopefully I'm right. But the paper isn't really about that. So they're not really trying to specify exactly how to fix it. In fact, as far as I know, this is the first time that there's sort of a comprehensive fix with a proof and so forth.
It's very nice that you were reserved.
Hi, if I understand it correctly, part of the problem is that with the subtype asserting wildcards, you have lower bound is a subtype of the wildcard, which is a subtype of the upper bound. And by transitivity, the compiler assumes that the lower bound is a subtype of the upper bound, even though it might not be the case. So do you know if it would be possible to solve the problem by preventing this transitivity rule in the case of wildcards?
Mm-hmm. So I don't think it's the transitivity per se. It's actually, like in the example that I showed at least, the issue isn't that the compiler is now assuming that T is a subtype of marker. In this case here, it's just that it assumes that T is a subtype of the newly introduced type variable. And that's enough. So there is actually no transitivity here, as far as I can tell. And I forgot to mention, like, this is where you can see, though, why I'm calling it subtype asserting wildcard. I mean, that's a term I made up, right? You could call it anything else, but basically, like, when this wildcard gets materialized, it makes sort of this assertion about what the subtyping is. And as far as I can tell, that's deliberate. Like, capture conversion is designed to do this, right? So that's okay, and it does that. It's supposed to do that. What I'm arguing is that's not the problem. The problem is we need to make sure that when we introduce these guys from a non-wildcard type, right, we do that knowing that we have a witness type. As long as we do that, this is fine. There's nothing wrong. There is nothing wrong with what the Java compiler is doing here. The issue is that it lets us introduce these wildcards from null without checking them. Does that make sense?
Okay. So maybe it's time to close the session. Let's thank the speaker again.